Yeah. Okay, thank you for coming. Today we have Jiequn Han, and the title of the talk is Generative Modeling Without Clean Data, Self-Consistent Transport Under Black Box Corruptions. Although I think maybe, yeah, I guess also extending measure dynamics beyond generative modeling. And Jiequn Han is a research scientist at the Center for Computational Mathematics at Iron Institute Simons Foundation. He conducts research on machine learning for science, drawing broadly from the methodologies and challenges of various scientific disciplines with a focus on solving high-dimensional problems in scientific computing, primarily those related to PDEs and generative modeling. He holds a PhD in applied mathematics from Princeton and dual bachelor's degrees in computational mathematics and economics from Peking University. And his research has been recognized with the SIAM Computational Science and Engineering CSE Early Career Prize, awarded by NLA to one scholar. So we're very happy to have Jiequn, and with that, just take it away. Thank you.
Hi, thanks for Carlos and Yuan's invitation and the introduction. So yeah, today I'm very happy to present some recent works for my collaborators and I. So without further ado, I will get started. So I guess the attendees of this seminar are all already quite familiar with generative models. Now it's like a dominant paradigm in generating many data modalities like images, videos, or even like protein structures brought by the success of AlphaFold3 and many works. One way to think about this general modeling is the following. Suppose we have many samples from an unknown distribution pi as a data set. We want to find a parametric form, a pi theta hat, such that this approximation density pi theta hat is close to the original target pi, and this pi theta hat is easy to sample. And one very promising paradigm to realize this goal is based on the idea of measure transport. Put simply, it's about transporting data from a base measure that is easy to sample to the target measure under certain ODE or SDEs, which are learned from data. So there are many famous models fall into this category, like score-based diffusion model, flow matching, rectifier flows, stochastic interpolants, etc. And one reason for the big success of these measure transport models is because it is formulated in continuous time, and such formulation enables a new algorithms and analysis of the correspondence between SDEs and the PDEs, or more specifically between the particle dynamics and density evolutions. So you will see this correspondence in more details in the later part of my presentation. For example, here is just one primary slide for the score-based diffusion model. We have two processes. You may have seen this figure many times, so I will make it short. We have the clean data, suppose at t equals 0, and the noisy data at t equals capital T. And the fourth process is about adding noise. And mathematically, we can prove by analyzing the Fokker-Polanyi equation. If we write down a reverse SDE in such form, then we can show approximately these two processes share the same marginal density at any intermediate time, so that it allows us to start with the noise at capital T and then simulate the data into clean data until t equals 0. And the key term in the reverse SD is exactly the term highlighted here, the score function, the gradient of the log density of the log density at any intermediate time t. So one nice property is that this score function under some simple Ford process or general linear Ford process can be equivalently written as something as a conditional expectation. So that conditional expectation, we know it can be interpreted as a minimizer as a regression problem. So that's why we can use the clean data set to construct a regression problems to learn this score. So that's the one of the big success of this score-based diffusion and many measure transport models. And So once we can learn, once we can utilize a large networks, many compute and data and to learn this score accurately, then it allow us to get new samples from the original data distribution, instantiated by the dataset pi. But one big motivation for my whole presentation today is that very often we are not only interested in getting new samples from original distributions, we are also interested that perhaps maybe the simplest task, but we also want to generate samples from related distributions. So here is just the two motivation scenarios. I call them both as adaptation. For example, if we use P naught x to denote the density from the pre-trained distribution, sometimes we want to sample a neo version of this density denoted by Q. So this kind of a neo procedure appears often in the statistical mechanics or related sampling tasks. So you can see the orange one is the original data distribution, and then by increasing the temperature by setting a gamma larger than one, smaller than one, we can get something that is more sketched, and you can also try to use a larger gamma to get like low temperature, which is like more concentrated distributions. And another perhaps more popular task is reward tilting. We want to tilt the original density P naught x by another term, which is always should be also always positive as a density. So we use exponential of reward function Rx to note this. So here just like just one slide for some more specific background of this reward tilting. So one way to think about this reward tilting task is from the Bayesian perspective. Suppose we have some additional observation y based on the related to the original clean data x from certain forward model y equals fx plus some noise. And then by the Bayes rule, we know the posterior distribution we want to sample should be proportional. The density should be proportional to product between the prior, which is implicitly defined by the general model, and then the likelihood. So this is one way to write down this reward function. And in the literature, this may be the first task people attacked for this adaptation task. And the one mainstream approach is trying to approximate or modify the reverse dynamics with certain heuristics related to the posterior scores. So this has been very successful, but there are certain uncontrollable errors in this approximation. And in terms of computation, if you look at this axis, these methods are usually very computer light. So you don't need, you just introduce some approximations, so they can be sampled very cheaply. And another task a lot of people are interested is something really as defined as a reward model. For example, you have human preference data for image generation, or in the drug design scenarios, you want have some additional desired properties for the protein structures generated. So you can use the reward function to tilt or to define these desired properties to induce the distributions toward the high reward region. And sometimes this reward model is complicated, so people have to use some fine-tune method to update network word to update the network weights again, essentially as modifying the reverse dynamics to achieve that goal. So this is like two basic scenarios and the two main ideas in the literature. But I would say the one limitation for the method on the left, this approximation idea, is that sometimes they work very well, but you cannot have any guarantee or analysis stating what's the resulting samples. So now I want to introduce a few recent works trying to improve this task. So the first idea is done by with my collaborator John Bruna from NYU. So we consider a very special case. If the reward function E is quadratic and well conditioned, which appears very often in the linear inverse problems. And for this special case, the nice thing is that we can develop a new sampling algorithms for the target distribution and show we have the guarantees for this new sampling algorithms. So the key idea is not modifying the reverse dynamics, but instead we want to modify the initial distribution different from Gaussian, but keep the same dynamics to make sure that the sampling process ends up with a new distribution. So here is just a schematic plot of this new idea. I'm using a two-dimensional Gaussian mixture as example. So here the top left is the prior distribution. It's two-dimensional Gaussian mixtures. It is very sketched. And suppose we have already learned a perfect score so that we can start with the initial Gaussian distributions and end up with this prior. Now, under the linear inverse problems, we want to sample a new posterior. It's still Gaussian mixture, but with different modes and different weights. Our theorem shows that instead of sample this posterior distribution directly, we only need to start with such an initial distribution on the right. This initial distribution is different from Gaussian, but it is much easier to sample than the true target posterior. So you can see it is much closer to the low concave density. So if we start from this new distribution from certain time capital T star and run the same reverse SDE, mathematically we can prove it will end up with a posterior distribution. So this is just an abstract illustration for this idea. If we start with Gaussian, we can end up with our prior pi. But if we can start with a new initial distribution from T star and run same as DE, we can end up with a posterior. So in the paper, we give a precise characterization when this new initial distribution becomes lower concave so that we can use MCMC to provably and reliably sample these new things. But I will not go into the details. This is the first idea I want to mention, which is different from the main ideas in the literature. And then if we go back to this compute axis, you can see, okay, as I said, the posterior approximation have certain errors, and in range 1 or 2 years, people began to correct these bias errors by certain sequential Monte Carlo procedure. So to put it simply, the idea of sequential Monte Carlo is that it is a particle method. In theory, it enjoys asymptotic convergence, meaning that if you have like infinite number of particles, it should approximate target distributions to high accuracy. But the reality in practice is the particle method will suffer from huge variance. So in the practical regime that we can afford to simulate particles, usually or very often you cannot observe any convergence because of that huge variance. So one wish is that can we develop some efficient inference time scaling method, just like inference time scaling meaning that increase the number of particles in this context, so that we can make the particle scaling gains observable for general diffusion model adaptations. So in a work recently accepted to iClear, we developed a new method called drift light about control the drift dynamics in the reverse process to enable inference time scaling of diffusion models. So this is done with a bunch of collaborators from Stanford, who's the lead author Eno did the summer intern with me in Flight last summer. So just as a preview, the key idea is to analyze the optimal drift and approximate efficiently within a linear space. So I think this work is a nice example to illustrate some main ideas, baseline ideas in the literature, and show what we can do on top of that with some optimal control ideas. So I want to spend a few more words on that. So here is a basic problem setup with a notation. So here I write down the folder process in a very general form with some with some drift u and standard Brownian motion. And on the right, we can write down the Fokker-Planck equations. And again, then we use v to denote the reverse process. So here I introduce a change of time in the reverse dimensions. So the generation process for the reverse part is always use time index t, and it is redefined from 0 to capital T. And similarly, we can write down the Fokker-Planck equations on the right. So the key point, as I already mentioned at the beginning, is that the drift in the reverse process and the drift in the prior process should have a difference of the log score. Okay, if it is satisfied, then we can make sure the generation process at terminal time t should be close to our original data distribution. Okay, so this is just a notation, and then we want to sample instead of from p0, we want to sample from some new target qt, either by the annealing task or in the rewarded task. So first thing we can use, we can utilize these two tasks in the same notation. So if gamma equals 1, it becomes the reward tilting. If r equals constant, it becomes annealing. And the usual way to design to solve this task is, given this target, the terminal conditions of the target, we specify certain distribution paths. So we only know capital T we want to end up with our target. Now let's say we design the interpointer path at the density level, so that Qt, when t equals capital T, it is consistent with our target. When t is 0, it is something easy to sample. And then our goal is, again, like the original prior generation process, to design some particle dynamics to track this new distribution path. Okay, so the simplest idea in the literature is called guidance. Okay, it's very simple. Okay, or because we already know the drift for the process is determined by the log of the prior density. So let's just replace the prior density with this new target density, and still takes the log of this new distribution path we designed. And then we can formally write down a candidate for the new reverse drift. So let's use the VQ to denote this new drift. So the first string questions we can ask, okay, under this new drift dynamics, will that track our distribution path, okay, faithfully? Okay, the answer is no, because if the answer is, then the problem is already solved. So by some analysis of the Fokker-Planck equation, okay, we can show, okay, the target density we write down will not satisfy the desired Fokker-Planck equations. So this is just one way to confirm the answer is no. To be more precise, okay, if we want to make sure the Qt is the solution of certain equations, then in addition to these Fokker-Planck equations, we need to add another multiplicative terms. And in the simulation context, this multiplicative term will correspond to a weighting potential function. So given the definition of this reverse drift Vt, we can write down the definition of this weighting function explicitly, where to make sure this is always like this equation always preserve densities, and this potential function will has a one nice property. It should be mean 0, and this integrand capital G we have the analytic expression, but I will skip that. So given these weighting equations as a generalized Fokker-Planck equations, how can we design particle dynamics? So that's the main idea of sequential Monte Carlo. Actually, instead of only simulate the IID particle dynamics in the original prior process, now we should augment the state xt with another log weight process. So here I'm only using finite particles from 1 to capital N. So the subscript I index denotes the particle index. And then you can see I will use the potential written from the original, from the previous slide to denote the dynamics of the log weight. So because we only have finite particles, so we normalize them empirically over n particles to design these new potential functions. And again, asymptotically, we can prove as number of particles goes to infinity, this joint particle and log weight simulation process will reproduce the original density function Qt we want to keep track of. So this is the main idea of sequential Monte Carlo. You can see we have a bunch of particles, we keep track of them with the weights. So we will first move the weight location, the weight states by the SDE. Then we will adjust the weights by the log weight process. So asymptotically, it is very nice, but one big limitation for this thing is that because we only have finite particle approximations, so if the variance of the weights is very large, then the weight will degenerate very quickly, losing any approximation property to the target. So what we can do, the starting point is that there's an additional degree of freedom in this sequential Monte Carlo process. So we can always choose different control, and the effect of the control can be always equivalently absorbed into particle weights. So here on the top, I'm write down the original Fokker-Planck equations. So you can see the left part is the Langevin dynamics, and the right part is the weight process. And now, if we want to modify the Fokker-Planck part or the Langevin part by adding another velocity field to the baseline heuristics from pure guidance, okay, with this BT, to make sure the equation is still satisfied. Of course, you can imagine we should change the right-hand side term as well a little bit. So we will define a new potential functions, and the difference with respect to the original potential is something related to the velocity BT we write down, okay? So nothing special here. The key questions we can ask is that what will be the best proposal BT here so that the right-hand side of the weighting process can be as simple as possible. In a simple case, the weight becomes a constant so that we don't need to simulate anything on the right becomes zero. Okay. So the main proposition in our paper is that we can characterize the optimal contour in the following sense. Assume it is curve-free, meaning it is a gradient of some scalar potential, then we can prove this potential function capital A should satisfy a Poisson equation, where Qt is the density we want to keep track, and the Gt is the potential function of the original baseline process. So in other words, if we can solve the Poisson equations, then we can find the optimal drift, and we can simulate the new process very cheaply. So how do we solve these equations? Okay, we can design different objective functions. For example, since one interpretation of this optimal drift is make variance of the weight zero. So we can directly take the variance of the weights as objective. So this is like the strong form of the PD equations. Or we know Poisson equations can be viewed as a minimizer of variational problems. So we can write down the original energy functions. So we can, if we can find the optimal potential AT, minimizing this potential, by calculation of variations, we can prove the minimizer should also be the solution of the problems. But one thing I want to comment is that either the variance controlling objective or energy control perspective objective, if we use neural networks to parameterize BT and AT and then optimize, it will be very expensive because you need to take a lot of backpropagations. And remember, we want to make sure our whole algorithm is lightweight. So another thing we propose in our work is that we want to restrict our control to be just a linear combination of a few bases. So the three bases here we write down is just the gradient of reward function, the prior drift, and the score. Okay, you can immediately realize this is just the same basis used in the pure guidance. So in other words, we are use a control ansatz as simple as the baseline pure guidance. The computation optimization is a very light overhead, as you can see, because we are only optimizing 3 linear coefficients of these things. It amounts to solve a very small linear systems. But as you see in the next slide, it is far more effective than the baseline of pure guidance. So that's the main idea of this work. So here you can see the illustration on the 50-dimensional Gaussian mixture model. The top left is the 2D slice of the ground truth. If we only use pure guidance, the measure distance, the MMT distance between the simulated samples and the ground truth is 0.9. And if we correct the pure guidance with sequential Monte Carlo, you can see the distance decrease. But if we use our variance control guidance procedure with a very lightweight computation, we can further reduce the errors to a very small number. So here on the bottom left, I'm showing or verifying the variance is indeed much better controlled compared to the pure guidance. So you can see here the bottom panel is the variance and top panel is effective sample size. Our variance control method, the red one or green one, the variance is much lower than the baseline. And on the bottom right, I'm just showing what I mean by inference time scaling. So here the x-axis is the number of particles and the y-axis is different error metrics. So you can see for the pure guidance or the guidance with sequential Monte Carlo, although in theory they enjoy the asymptotic convergence, but as long, even for the number of particles as large as 2 to the 15, okay, you can see that the variance still dominates the performance. So there's no improvement as you further increase the number of particles. But in contrast, for our method, as we further increase the number of particles, we can consistently observe the improvement. And we also show a protein example, a conforming example from some protein general models. And if we apply our idea, we can see on different metrics, it gets improvement over different baseline methods. So this is the second idea I want to mention for adaptation. And the third idea, the last idea I want to mention regarding the adaptation is slightly different. So the first two works I have mentioned so far is always about adapting one specific distributions. But in many large-scale applications like image generation or protein generation, it is always a conditional generation models. You always have some conditional vector to define your distributions, like text prompt in your image case, or sequence conditions in your protein condition case. So there's another aspect as the conditional vector in your whole generation models. So in the protein generation case, our goal of adaptation is to generate a protein conformations that are physically plausible, which is determined by the prior, but also consistent with some experimental measures, as you see in this animation. So in this new range work with my colleagues from Flatiron, we explore another idea, not about adjusting the state X, but about optimizing the conditional embedding in defining this new distribution. So the high-level idea is trying to optimize the conditional embedding to shift the prior toward closer to the target distribution. Okay, so this optimization actually, again, is very expensive. So we have to introduce certain heuristics. I will not go into the details, but again, if you compare this method with the baseline DPS method as a guidance-like method with a fixed prior, in the protein generation task, we found that our embedding optimization method achieved better reconstruction quality, and it is much more robust across different type of parameters, especially the learning rate needed in the DPS scheme. And because of this more robustness, our optimization embedding optimization method also allows a faster inference with fewer diffusion steps. But due to the time limit, I will not go into the details. If you are interested, you can take a look of the paper. Okay. So now I have introduced a few ideas in the adaptation, and you can see the the starting point of all these models is all these works is assuming we already have a pre-trained model, which is obtained from pre-training on a large clean data set. And we assume the pre-trained model defines a very strong prior, such that we can start from there to define new adaptation tasks. Okay, this is very useful, and with the same pre-trained model, we can use it for different adaptation tasks with the similar methods. This is just a cartoon for the inverse sampling, for the posterior sampling problems. Once we can have a clean general model for clean data, then once and given a new blurred images, we can utilize all the techniques explored in the literature to get a clean sample. And as I said, here I'm applying it to the blurred images, but you can apply it to different cropped images with same methodology. That's why it is a powerful technique. But the key point I want to highlight in the remaining part of the talk is that this assumption is not always valid in many scientific applications. Okay, very often we may only have access to a lot crop data, but we do not have any access to the clean data. Okay, so this is the new task we want to explore. Okay, suppose you only have a data set, but this data set consists of many cropped samples, and you know the corruption process of this data. Then you can still ask, can we get a judgment model for the clean data on the left? Okay, so we term this new task as inverse judgment modeling. So actually, this kind of applications appear in many scientific disciplines like cryo-EM, medical imaging, particle physics, astronomy. Okay, in that case, if very often you may only have a very small fraction of clean data, or you may not even have any samples of clean data. Instead, you can try to use your measurement device to collect a lot of measurement data as indirect data. And you can see as we continue to have better measurement device, we can get more and more data as a larger and larger data set. But we hope we can get a gentle model for the clean data so that we can again go back to utilize a lot of adaptation techniques to solve different to solve different scientific problems. And I will say this is not a new problem. Actually, it has been explored in different scientific disciplines without general models. But again, with the new success of general model, you can see some new opportunities, and it is gaining growing interest in optimization and the machine learning community. That's why we also recently got interested in this new task. And with the collaborators from NYU, we propose a new method based on the self-consistent stochastic interpolant, so that we can learn a general model from the clean data only using a black box simulator for the model and the corrupt data set. Okay, so this is the overview of this new task. Let me first make it more precise as a setup. So suppose we can observe IID measurement data 1112 YN as a data set. So these measurement data are generated from some latent clean data samples x1, x2 to xn through a stochastic simulator, yi equals capital F xi. So this F it can be stochastic, so you can think it induce certain conditional distribution y conditional on x. Okay, so if we use pi to denote the data distribution of the clean data x, and we use mu to denote the distribution of observation data y. So you can think our forward model capital F defines some operator k that mapping the clean data distribution pi to the observation mu. Okay, so In this sense, our inverse generative modeling is about learning a generative model for pi given samples from mu and the black box access to the simulator capital F. Mathematically, you can think it is equivalent to solve the distribution level equation k pi equals mu, which is a linear equation but defines over a huge space. It is a density space. So as long as your data dimension is above 3 or 5, okay, you cannot imagine solving this equation at the density level. So we hope to solve this inverse problems at the distribution level with some generative modeling tools. And as a starting point, without loss of generality, we will assume that both observation data and the clean data live in the same space. So the Y lives in the same space of X as a subset of some Euclidean space. In fact, actually, it is not a big assumption because you can always design some joint space between X and Y to define a new forward operator over that joint space so that this assumption always holds. Okay, but using this notation will make our explanation much easier. Okay, so the main generative model tool we use for this task is stochastic interpolant. So then let me first introduce it the notation a little bit. Assume in the classical setting we have clean data. Okay, suppose we have clean data. So in other words, we can sample from both pi and mu. Okay, then the idea of stochastic interpolant is that we can sample something as a pair of a joint density of pi and q as x0 and xy, when x0 is the clean data side, x1 is observation data side. And we can also additionally sample some Gaussian noise z and construct an interpolant it as a linear combination of x0, x1, and z. We just need to make sure those linear coefficients alpha t, beta t, gamma t satisfy some boundary conditions so that when t equals 0, it has the same distribution of pi, and when t equals 1, it has the same distribution of mu. So given this interpolant, if we define the velocity as the expectation of the time derivative and also a score as the expectation of the noise z conditional on the it cos x. So with the very similar mathematical tool as in the general score-based diffusion, we can show if we consider a reverse time dynamics starting from t equals 1 back to t equals 0. If we define the particle dynamics using the same as this SDE, then we can prove if it starts at t equals 1, it is distributed as mu. Then when t equals 0, the state will have the same distribution of pi, so that we again achieve the goal of general modeling from mu to pi. So that's one comment. Here for the simplicity of notation, I'm using SDE to unify both ODE generation and SDE generation. If you choose your diffusion coefficient epsilon t to be 0, then this reverse dynamics becomes ODE. But you can also choose non-zero epsilon t to allow SDE generations. Okay. And the training for this stochastic interpolant is also very similar to diffuse score matching, because both unknown functions b and g admits a conditional expectation representation. So you can design a regression objective and use the data to sample IT to optimize these two objective functions to get the approximation. Okay, so this is just a setting for the clean data, and here is just an illustration borrowed from the original paper. So again, assume t equals 0 is the clean data. Here is the white colored flowers, and the right is the purple colored as some observation. Okay, so by choosing different interpolations, you can have different interpolation process or generation process, and the top two you can think it as our inverse general modeling. So in our inverse general model setting, you assume you can only observe the purple colored flowers, and you know, okay, how your color filters transform your white color into purple color flowers. the question is, unlike the classical general model setting, you don't have any data at t equals 0 to start with as a sample of target distribution. So that's the main challenge we need to solve in our inverse general modeling setting. But there exists one simple and heuristic idea. Okay, since the challenge is no sample to start with, let's try to make a guess for this target sample. Okay, and then we can design some iterative scheme, hoping it will converge to the to the target resolution as a fixed point. Okay, so let me make it more precise. Okay, again, this is the reverse process. Assuming we will start from t equals 1 as observation data that we have, and we wish when t goes from 1 to 0 backwards, it will end up with some samples similar to the target distribution pi. And in this reverse process, the main functions we want to determine is the drift b and the score g. Okay, so we use capital theta to denote all the unknown functions, which will be approximated by neural networks. So given the choice of these vector functions, then it defines a backward transport map, capital phi theta. Okay, this capital transport map transport samples from t equals 1 back to t equals 0. And this transport can be stochastic, conditional on the additional realization of Brownian motion, but then to change this concept. And then given this transport map, it also induced a new distribution at the data's clean sample x side by pushing mu back to a pi, right? So given this notation, our ideal goal is trying to find an optimal parameters theta star, which can be defined as the ground truth case if we have access to both clean data pi and corruption data mu. Okay, so in other words, we can use a consistent condition to characterize the optimal theta. So if we have optimal theta star, then we can first use the transport map to push data from y back to x on the left, and then if we further apply our forward simulator f to this data, and at the density level it is a kernel k, it will become identical to mu. So this is our consistent condition. So here I'm using an illustration to explain what I mean. We have samples from mu, and if we have a theta, we can define transport map to define a new distribution pi theta. And given this pi theta as a guess for the clean data, we can construct an interpolant between pi theta and k pi theta. K pi theta can be sampled from calling the simulator. So we can learn along this new interprocess to update the parameters theta, and hoping it will converge to the ground truth. This is what I mean by self-consistency. So to make it more precise, given our current guess of the parameters at iteration k, so here k is about the iteration, we can construct a following stochastic interpolant with index k plus 1. The data set is obtained by pushback on the data y under this transport map phi theta k. And the new observation, simulated observation, is defined by further feed back this clean data, get the clean data into the simulator f to get a new observation y. And this is our new interpolant. And then we can minimize theta k plus 1 respect to this new interpolant. So this is what I mean by fixed point iteration. It will, given theta k, we first generate samples to define the interpolant at iteration k plus 1, and then we minimize the functions to get the parameters corresponding to index iteration k plus 1. Okay. So in terms of the pseudocode, if you are familiar with stochastic interpolant, you will find our code actually implementation is very simple, almost as simple as original code. So here the inner loop is just a standard optimization for the stochastic interpolant. You sample data on the left, on the y, you sample the data on the x side, and sample new y quota on the y side, and then construct the interpolant and the SG update. We just design another outer loop iteration about updating the parameters. So the whole algorithm becomes a bi-level iteration scheme. The outer level is the fixed point iteration, and the inner level is just about optimization with the stochastic interpolant. So the simplicity of this pseudo algorithm is why we can try to combine it with the standard general modeling training to solve the tasks, or it's why we can scale our algorithm to much larger high dimensional data set. Okay, one last comment before the numerical result is that if you are familiar with the expectation maximization method in statistics, you may sense something similar. So actually, in a paper from 2024, there's a group of researchers using the classical EM approach to solve this inverse general modeling task. So here it is also iteration idea, but what they are iterating is about the prior guess. Okay, using the language of expectation maximization, the E step is about given the counter prior pi k, I can generate new posterior samples with using the Bayes rule given my observation y. Okay, then get new posterior samples, I can update my prior to match this new data set. This is the maximization step. So you can see this in spirit is similar to our procedure. Our sampling process of this new interpolant is like the E step, and our minimization is also about minimization the general modeling functions in the classical setting. But I want to highlight the key difference with respect to the expectation maximization approach. If you want to use the expectation maximization approach, first you need to make sure you have access to the likelihood to define your Bayes rule. And second, as you see in my first part of talk, reliable posterior sampling actually is not an easy task. That's why in the early work, people have only used this idea to solve some linear inverse problems because you have a more reliable posterior sampler. But the benefits of our self-consistent stochastic interpolant is that we only require a black box simulator. We don't need the likelihood form for this simulator, so that this whole methodology is applicable to nonlinear forward model or even non-differentiable forward model and the non-Gaussian noise, as you see in the numerical result. Okay, so yeah, so here is the numerical result. So here, this is a task about CIFAR dataset. Each column, each panel is about one corruption model. So here is the random masking. The middle is the Gaussian blur, and on the right is a non-linear motion blur. So for the model, we need to train our stochastic interpolant. So we train the three different. We apply our method 3 times for 3 different crop data sets. On the top, you can see the original clean image, and in the second row, you see the cropped image, and in the third row, you will see our guessed clean image after we apply our procedure and convergence, convert to a few iterations. So you can see it is very similar to the clean images. And on the last row, we are presenting the performance of DPS method. But keep in mind, this method is a posterior sampling method. It first assumes you already have a pre-trained general model pre-trained on the clean data set. So in other words, DPS utilize much more information from the pre-trained model, but compared to that baseline, you can see the DPS sometimes have some artifacts in the restoration, But in contrast, without any access to the clean data, our method can still restore the cropped image quite well. So here is just some metrics from the table. On the left, you can see the performance of restorations. So you can see we compare our method with the DPS, which utilize the pre-trained model on the clean data. And we also compare our performance with an oracle model, again, assuming access to both clean data and cropped data. So you can see our method matches or even sometimes exceeds the restoration performance of models trained on the clean data. And then in terms of the final generation performance, if we compare with several existing methods from literature, our consistent interpolant achieves the best generation performance as well. And actually it is close to the performance when you have clean data. So here is just another corruption model on the celebrity data set. So here the folder model is a JPEG compression. So JPEG compression is a non-differentiable nonlinear model with one hyperparameter, the quality factor from 0 to 100. So the lower the worse. So if we train our model with access to the compressed data from the factor from the quality factor from 10 to 50, and you can see even with a very low quality data, we can learn a good transport model. So if we apply our transport or restoration on different on images with different compressed quality, it can achieve quite good restoration performance. And this is the final example on a scientific data. So here the data is no longer 2D images, but 1D frequency data from the cosmology observation. So we consider two heuristic for the model. One is that you have high spectral resolution, but the signal noise ratio is low. And on the right, you have low spectral resolution, but your signal to noise ratio is high. So for the models, we apply our technique. You can see it achieves much better performance than standard method, only applying inverse solver on the individual level. So here, I think a philosophy I want to convey is that right now in the classical scientific computing inverse problems, you have many methods like solving a sample level, individual level inverse problems. But here we want to argue if you can solve distribution level problems by leveraging all the data you have jointly, potentially you can get much more performance. Although this is a much harder problem, but right now the large scale general modeling make it possible. Okay, within the last 3 minutes, I just want to briefly mention some theoretical analysis we have for this stochastic interpolant. Basically, we can have consider one simple setting, the added Gaussian noise example, which we can have an analytical analysis. So here, assume our prior is a Gaussian distribution, and our forward model is just a standard Gaussian noise. And if we initialize our model as another Gaussian model with initial guess, with the mean and the covariance, and define a linear interpolant, then we can show in our fixed point iteration, all the intermediate iteration is also a Gaussian family. So that's why we can try to characterize the iteration of B and sigma along the iteration. So to be more precise, we can write down the convergence rate for the iteration, and you can see it admits a linear convergence. And from this linear convergence, actually we can draw many interesting conclusions for this special model. The first thing is that, okay, if you try to optimize the upper bound, the linear rate, the convergence rate for this case, you will find actually the fastest convergence is achieved if you specify epsilon equals 0, corresponding to the ODE case, which is sometimes observed in our numerical results for imaging. We also find sometimes ODE convergence fastest. Second, if you apply the EM algorithm I just mentioned to these problems, you will see the convergence is identical to to our result for choosing epsilon equals 1. Okay, so that means in the low simple in the simple regime where the eta is very small, the signal to noise ratio is low, then our method is indeed converging faster than the EM method because there's a difference in terms of convergence rate. And even in the non-simple regime, if we numerically write down the convergence, you can see our ODE approach will converge faster than the EM approach. And finally, this is just example in the special Gaussian case. And in the paper, we also provide some abstract results. If we have certain assumptions for the condition number of the following model, we can prove the convergence for both in the sense of both W2 and KL. And at least, okay, the assumptions is a bit of abstract, but at least you can verify in this special Gaussian linear case, these assumptions are satisfied. Okay, so I think I will stop here. Okay, right time. As a summary slide, the measure transport-based general model allows us to model complex data distribution from data sets as some dynamical systems, and they can also be adapted to solve related sampling problems by modifying the dynamical systems. And in the second part of my talk, I basically mentioned that when clean data are unavailable, we can still learn a measure transport prior model from the cropped observations and the forward simulators by enforcing a self-consistent condition. So, and we believe this will enable many scientific applications. Okay, so I will stop here. Thank you for your attention.
Thank you, Jiequn. That was a great talk. Yeah, maybe let's open the floor for questions. If no one has a question, I have a few. Oh,
Sure.
yeah. Let's see. Okay, so there's an I can ask the question, or if you want to unmute yourself, you can also go ahead. Oh, sorry. So I'll ask the question. So Anar is thanking Jiequn for the talk, and he would like to dive deep into embed opt. So he says if he remembers correctly, it optimizes the pair former embeddings, which encode sequence and coevolution information. But for cryo-EM, the experimental signal comes from 2D particle images, not from the sequence. And the question is, have you considered defining the reward directly on 2D particle images rather than on the reconstructed 3D map? And if so, do you think that the embedding space, which is fundamentally sequence derived, still provides a useful manifold for steering towards conformations consistent with raw image data?
Okay, that's a very good question. Yes, you are right. So our current setting, experimental setting, is trying to using the reconstructed 3D map to define the reward, so that given the current X, we can directly define the reward by comparing some distance. You are right. If we only have 2D measurements, definition of reward function is not such easy, because it's also about how to align the 2D projections or with the original 3D configurations. So in other words, the reward function is much more complicated, or even maybe non-differentiable. So you are exactly asking one question that we are working right now with my collaborators. For those two, if we only have 2D images, can we still design some useful reward functions so that we can apply our steering techniques either on for the coordinate X part, or for guiding the embedding part, as I mentioned in our work? I think it is the open questions, but I'm being optimistic. I think it's still possible to write down some reward functions respect to the 2D images. And the second question is, do you think the sequence-based embedding is still a useful manifold? I think so, yes, because it's still about the protein configurations, and I think the MSA type thing may be limited, but it would be a useful starting point. But another comment, I guess, yes. I think another interesting viewpoint brought by our embedding optimization work is that it can go back to force us to think in our designing of pre-training, can we also better designing the embedding component so that the embedding functions optimized in the pre-training allows easier and more flexible steering in the post-training case. I think that's a very new open questions and worthwhile to explore. So yeah, so that's my thoughts for your question.
Okay, and then Anar is thanking you.
Mm-hmm.
If there are no other questions, I'll go ahead with a couple. So how many iterations did he do for the outer loop?
Oh, for the last part, right? That's
yes,
a good
yes,
question.
for the last part.
So I think it depends on whether it depends on how many steps you do in the inner step.
Okay.
So conceptually, I introduced as fixed point iteration. So the inner loop is defined as a minimizer of the interpolant for the illustration. But in practice, you don't need to do that. It will be not efficient in the early phase. So in the real code implementation, we actually do not set the inner loop iterations to a very large number. It can be as small as like 10 or 20, then we just keep iteration on the outer loop.
Right.
Yeah. And another comment, if you specify the inner loop as a special case, then it's something similar to like stop gradient.
Right.
Yeah. So, but we find something like larger than 1, but as a modest number, like leads to the more efficient performance.
And in terms of data set, how big of a data set do you think is needed? Because I'm assuming that in this case you need a substantial amount of data since you're basically pretending the flow model at every iteration, right?
I agree, but I think the additional factor is not huge. It's something modest, like factor maybe 10, something like that. Actually, in our case, we utilize we use the same data set as the CIFAR 10, so you can see it is.
Oh,
it's not much. It's not much, but for more singular or yield post forward models, you are right. It's possible that for sure, there's no doubt you need more data or more training compared to standard clean data training. But I think that the gap is not huge. It's something moderate.
I see. And is there a way, like, or an easy way in which you could, because you showed a baseline which was based on using a pre-trained model. Is there a way in which you could combine both, where you say you have like a pre-trained model that's somewhat okay but not perfect, and then
for sure. That precisely. So this kind of thing can be naturally integrated in current case. For example, in our code implementation, we start our iteration from the naive random neural parameters. So we without any knowledge, but if you already have a like low quality generative model or low quality images, you can always pre-train on that to get an intro guess for your generative model, and then apply our fixed point generation. So I think that will be reality in many cases. So in other words, in our code, we test its performance in the extreme case, random initialization. But in practice, if you have any knowledge or even pre-trained or whatever model, you can always simulate like a much higher. You can always have set a much better starting point. You are right.
Okay, there's a question
and
also by.
That's about initialization, nothing special.
Okay. But there's another question on how does the method handle mismatch between simulator noise and real world noise, meaning models but misspecification?
that's a wonderful question. Yes, yeah, I have to admit, right now our work assume we have a perfect simulator. So in other words, there exists one perfect, one ground truth, at least in the infinite example case, match our observation. Yes. So in order to the model specification, I think we need to consider the inverse problems at another larger level, involving some uncertain quantification of the parameters. So I mean, one way you can think is that suppose you have for the model, but you have a few unknown parameters. You can define your inverse problems at the larger level, both jointly including data and these unknown parameters, and then you can do like uncertain quantification for the unknown parameters as well. In the parametric setting, that's one way I think possible. But in general, yes, if we have some miscalculation how to make it robust in this current pipeline, I think it's a very interesting and important questions. Yeah, thanks for the great question.
And okay, maybe one last question that has to do with the second word you presented. So if you want to steer like a text condition model or a model that's conditioned on something, would you set the optimal coefficients individually for each conditioning, or like would you learn them for all of them? For like would you use the same coefficients for all the conditionings?
That's a very good question. So I think to make it useful, maybe learning a common coefficient will be the most easy. So that in the simple, because once you have that, then you can use very few particles. And so in other words, yes, I think that's a very good question. So I think it's possible in the pre-training, in the middle training phase, you apply our technique to different text prompts and simulate many particles to optimize the coefficients, so that in the final inference time, you can use a common good coefficients.
I see. So the way you run the experiments was on unconditional models.
Yeah. In the way I really this unconditional model. You are right.
Okay.
Yes. Yeah, but we do observe some shared pattern of the coefficients, because you can imagine when the coefficients are close to clean data, the guidance actually is quite good, because that's a theory, right? So the main point is that we can find the coefficients that are much more useful on the early phase, but I think the magnitude or the overall trend, they are shared across different instances. So I do think it's possible to find a common linear coefficients applicable to different conditions.
Okay. So I think that's all on my side, and I think there are no more questions online. So with that, let's thank Jiequn again. Yeah, this is very, very useful. Thank you.
Thank you. Thank you.
Yep,
Bye.
Bye.